This is Chapter 1 from General Organic and Biochemistry 9th edition by Denniston. In this video we're going to go over the first couple of sections of chemistry. So topics that are covered in this chapter. Begins with a lot of definitions. What is chemistry? What is matter? What are the steps of the scientific method? But as far as the concepts we're going to dive in more deeply in Chapter 1 is distinguishing between chemical and physical properties and chemical and physical changes, intensive versus extensive properties, classifying pure substances and mixtures as heterogeneous or homogeneous, and then getting into the numbers. We're going to look at how do you figure out how many significant figures is in a number. How do you write a number in scientific notation or take a number out of scientific notation? How do you interpret scientific notation? We're going to look at how do we round numbers when we're doing a math problem. If you're adding or subtracting or multiplying or dividing, how do you know where to round your final answer? And then we're going to look at unit conversions, both converting temperature scales, Celsius, Fahrenheit, and Kelvin, and converting in and out of standard and metric, so quarts to liters, inches to centimeters, as well as converting around metric units, centimeters to meters, kilograms to milligrams. And the last part of Chapter 1 is calculations of density. How do we calculate density? How do we use the calculation for density to determine mass or volume of a substance? So let's first look at classifying matter first. So matter can be classified as either a pure substance or a mixture. Pure substance has only one component in it, whereas a mixture has two or more pure substances mixed together, but there's no chemical reaction when they are mixed. They're just physically mixed together. So examples of a pure substance then would be elements and compounds. Elements, if you look at the periodic table, you see all the elements. We have hydrogen, helium, lithium, oxygen, nitrogen. If it just contains one element from the periodic table, even if there's more than one atom of it, such as O2 is two oxygen atoms together, it is going to be an element. There's just one element present. Compounds, on the other hand, have more than one element present. For example, salt. In this case, we're referring to table salt. Sodium chloride, NaCl, contains the element sodium and the element chloride, and they are not physically mixed together. They are chemically bonded to one another, and that is a compound. Both elements and compounds are pure substances. Water is a compound, H2O, two hydrogens chemically bonded to an oxygen. That is a compound, and it is a pure substance. So elements cannot be changed into any simpler forms by a chemical reaction, while compounds can be broken down into their elements with a chemical reaction, but not a physical reaction. So looking back at those mixtures, mixtures are physically mixed together, but each individual substance, whether it's an element or compound, is going to retain its own identity. They're just physically mixed together. And the mixtures can be further categorized as homogeneous or heterogeneous. Homogeneous, the prefix homo meaning same, has the same uniform composition throughout. So the particles are well mixed, thoroughly intermingled, whereas heterogeneous has a non-uniform composition, random placement. Generally, with a homogeneous mixture, you can see the individual components because they have not thoroughly mixed together. So an example of a homogeneous mixture, air. The air we're breathing right now is not a pure substance. It's a mixture of different gases. Mostly nitrogen, some oxygen, carbon dioxide that we produce. Depending on how humid it is, there's going to be some water and trace other gases, but it's a mixture of these gases. ethanol in water. So if I go to the store and I buy a alcohol mixture, it's generally going to say something like, 80% alcohol. That means it's 80% alcohol and 20% water. But if I were to look at that bottle, I wouldn't be able to see the individual components. Water and alcohol would be thoroughly mixed together. How, on the other hand, if I grabbed a bottle of oil and water, say I'm getting salad dressing, I will be able to see the oil and water separately. Oil and water don't mix, so that you get a heterogeneous mixture from them. Salt and pepper mixed together would be physically mixed. You could see the grains of salt and the grains of pepper separately. So that would be an example of a heterogeneous mixture. If you can see the separate components, then they are heterogeneous, not homogeneous. Properties can be classified as physical or chemical, and physical properties and physical changes go hand in hand, just as physical or chemical properties and chemical changes go hand in hand. A physical property can be observed without changing the composition or identity of a substance, and a physical change is one that there is some recognizable difference in the appearance, however, its composition was not changed. Most common physical changes are physical state changes, such as going from solid to liquid, melting an ice cube. So say I have a cube of ice, so water, H2O, and it's solid, and I melt it. Now it's liquid, but it's still H2O. I did not change the composition or identity of it. It is still H2O. It just went from being solid state to liquid state. So changes of state, melting. So here I have solid water. These are water molecules. The red ball in the ball and stick model is an oxygen. The two white ones are hydrogen. So water that is solid state, water that is liquid state, and water, this is water vapor. Water that is in the gaseous state is still H2O. Going from solid to liquid to gas is not changing the identity. So these are going to be physical changes, melting and vaporization, boiling, etc., are physical changes. Chemical changes, on the other hand, will result in changing the identity of the substance. So a chemical property is one that results in a change in composition, can only be observed through chemically changing, having a chemical reaction. So, for example, let's look at a couple of properties here and identify them as being a physical or a chemical property. Color. Can I observe the color of an object without chemically or physically changing that? Sure I can. I can look at a red ball and observe that it's red and I didn't change it at all. So color would be a physical property. Flammability. Can I observe at what temperature paper will burn or combust without chemically changing it? Well, no. The only way I can observe that is by, burning it. And if I burn paper, do I still have paper? No, it has been chemically changed. It is no longer paper. So flammability would be a chemical property. Hardness. Can I observe how hard something is without chemically changing it? Yes, so that would be a physical property. Odor. Can I observe something's odor without chemically changing it? Yes, I can observe odor without chemically changing it, so that would be a physical property. Taste. Can I observe something's taste without chemically changing it? Well, this one's a tough one. This is probably the trickiest out of all of these. And an argument can be made either way. I would argue that it is a chemical property because in order to observe something's taste, you have to put it on your tongue. And we don't observe the taste actually until our saliva starts breaking down that substance and through a chemical process. So I would make the argument that taste is a chemical property because we observe it through a chemical change. That is the first step of digestion, our saliva in our mouth starting to break down that substance. So that is classifying things as either being a physical or a chemical property. Now, physical or chemical changes, look at this one. Boiling water becomes steam. Well, that's just a state of matter going from liquid water to vapor water. And we said earlier, any change of states of matter are going to be physical changes. So this is a physical change. Butter turns rancid. So rancid or spoiling here. This is the first step in a decomposition. It is decomposing from butter into something that is rotting. Anything like that is a chemical change. It is no longer butter. It is going through some sort of chemical change, decomposing. It is rotting. So this would be a chemical change. Burning of wood, well, just like our example earlier of burning paper, burning wood is a chemical change because it will chemically change the wood into something else. Mountain snow melting in spring. Well, again, that's just a phase change. It is melting, going from solid to liquid, so that's going to be a physical change. Decay of leaves in winter. Just like the butter turning rancid, this is a decomposition. This is a rotting. This is a chemical process brought about by microbes breaking apart the chemicals in the leaves to form, well, whatever's left over from decaying leaves. Generally, we recognize that as just humus, dirt, basically. So that would be a chemical change. So being able to categorize things as chemical or physical properties or chemical or physical changes. So this is more than just defining it. You'll see questions on the test that are asking you to apply definitions. So apply the definition of a physical or chemical change to identify what's going on. In this next slide, we'll look at intensive versus extensive properties. Intensive properties are those that do not depend on how much substance you actually have. So for example, color or melting point. If I had a bucket of red colored liquid and I poured half out, well, it would still have the same color. So if the property did not change, that property is an intensive property. Melting point. If I have a, say, 2-inch by 2-inch cube of ice, at what temperature is that going to melt? Well, here in the US we use Fahrenheit, so to use a number you're more familiar with, the freezing point and melting point of water is 32 degrees Fahrenheit. That's the temperature at which any lower than that, and we have to start worrying about ice accumulating on the roads. Any higher than that, and we don't have to worry about ice. So that is the melting point of water. If I had a 2-inch by 2-inch cube of water, it would melt once I go over 32 degrees Fahrenheit. If I had a 2-foot by 2-foot block of ice, would it still melt once you go over 32 degrees Fahrenheit? Yes, it would. So that was an intensive property. It does not depend on how much you have. Extensive properties are those that do depend on how much of the substance I have. That block of ice, if I had a 2-inch by 2-inch cube versus a 2-foot by 2-foot, the mass and volume of those two cubes would differ. So properties that differ when you change the amount you have are extensive properties. Next, we're going to talk about units. So this is starting section 1.3 of your textbook. So units, what are units? In chemistry, we very rarely have numbers associated with properties that do not have a unit that go along with them. Chemistry is a quantitative science, meaning a great deal of it deals with numbers, quantities, and those numbers mean nothing if we don't have units that go along with it. If I just come along and say, I need 15 water, you're generally looking at me weird thinking, well, you're missing something there. 15 what water? 15 gallons of water, 15 cups of water, 15 pounds of water? I need a unit, otherwise the number means nothing. 15 by itself means nothing if I don't put a unit in there and tell you, well, oh, I meant 15 milliliters of water. Well, that's a big difference from 15 pounds or 15 gallons, so we need a unit in there. The English system is the system that we use here in the U.S., and it's not very functional because the units are very unrelated. It's difficult to convert from one unit to another because the conversion factors don't follow a set pattern. For example, 1 foot is 12 inches, which is a 0.33 or a third of a yard, or 1 over 5,280 fraction of a mile. None of these numbers have a set pattern to convert between them, which is why it's so difficult to convert from one unit to another in the English system. Scientists and most of the rest of the world use the metric system. The metric system is a set of units that are related to each other decimally, or deci means 10, by a factor of 10. So the units can be related by a power of 10 to one another. So in the metric system, the unit for mass is a gram. That is the standard unit. Compared to the English system, which uses pounds, there are 454 grams in every 1 pound. Mass is a measure of the amount of matter in an object. It must be measured on a balance, not a scale. Scale is what we measure weight on. Weight is not the same as mass. Weight is mass times acceleration due to gravity, which is why you do not have the same weight here that you would on the moon, because the moon has a different factor of gravity. Mass, on the other hand, is independent of gravity. You have the same mass here that you would on the moon because you have the same amount of matter. So mass must be measured using a balance, which measures mass, not a scale, which measures weight. Length. In the metric system, the standard unit is a meter. 1 yard and 1 meter are fairly close to each other. If I looked at a yardstick and a meter stick from far away, I may not be able to tell which one is which, but a yard is slightly smaller than a meter. 1 yard is equal to 0.914 meters. Volume. The standard unit for volume is a liter. Quart is the common English unit. So if I were to go to the store and say buy a quart of heavy cream, a quart, which can also be called a quarter of a gallon, is equal to 0.9461 liters. So again, slightly smaller than the metric unit. Time. The metric unit uses seconds, so that's the only one we're probably very familiar with. Liters and meters, not quite as familiar, other than maybe 2-liter soda bottles here in the U.S., but the rest of the world, for the most part, with the exception of a few countries, uses the metric system, and in science we will be using the metric system so that we can use those powers of 10 to convert. So what are those powers of 10? We have prefixes based on the powers of 10. For example, from the base, deca means 10. So a decameter is 10 meters. Kilo means 1,000. So a kilometer or kilometer is 10 to the third or 1,000 meters. Deca means 1/10 or 0.1. So a decimeter is 1/10 or 10 to the negative 1 meters. Milli means 1/1000 or 0.001. If you're not familiar with going in and out of fractions and the decimal system, go ahead and try plugging some of these into your calculator so you do get familiar. 1 divided by 10 will give you 0.1. 1 divided by 100 will give you 0.01. 1 divided by 1,000 will give you 0.001. 1 divided by 1,000,000 will give you 0.000001. That is micro. Nano is 1 divided by 10 to the 9th, or 10 to the negative 9th. So also getting familiar with scientific notation there. We can use those prefixes to convert in and out of the metric system. Now, volume and length are interconnected. We probably are familiar since maybe 8th grade geometry that the volume of a cube is its length times its width times its height. So I can measure the length, width, and height of a three-dimensional object and get its volume from there, length times width times height. So if I had a cube that was 1 decimeter, remember deca means 1/10, so 1/10 of a meter, 1 decimeter on all sides, so a perfect cube, all same on each side. 1 decimeter times 1 decimeter times 1 decimeter would give me my volume, or 1 decimeter cubed. 1 times 1 times 1 is 1. Decimeter times a decimeter is a decimeter squared, times another decimeter will give us a decimeter cubed. 1 decimeter cubed is the same unit as 1 liter. So if I had a box that was 1 decimeter on each side, that would give me a volume of 1 liter. Likewise, say I took 1/10 of that decimeter, that is a centimeter, or 1/100th of a meter, and I made a little cube that is 1 centimeter on each side. So that would have a volume of a centimeter times a centimeter times a centimeter, or a centimeter cubed. This volume is equal to a milliliter. So a centimeter cubed, which you may have heard called a cc when you're looking at, say, volumes of small amounts of liquid, say pulling up a amount of liquid medication in a syringe, and you may be told to pull up 2 cc's of the medication. That means 2 cubic centimeters. cc stands for cubic centimeters. And that is the same unit as a milliliter. So 2 cc's of a medicine is the same as 2 milliliters of medicine. These are actually the same unit. So volume and length are interconnected units. Now we're going into section 4, significant figures. Significant figures are the digits in a number that have or give you information about that measurement. How do we determine how many significant figures are in a number? Well, if you were the one who took the measurement, the device you use to measure that or take that measurement would determine how many significant figures are in there. So how much uncertainty you have depends on how accurate or how precise that device was. So if I am measuring distance with, say, a ruler that only has marks for every centimeter versus a ruler that has marks for every millimeter, the ruler with every millimeter marks would be able to have more significant figures than the ruler that only had a mark for every centimeter. Or if I was measuring the mass of an object and I put it on a balance that only went out to a 1/10 of a gram versus I put it on a much more precise balance that went out to every 1,000th of a gram, that would change how many significant digits I had in that measurement. So here's the example of a ruler that only has marks at every centimeter versus one that only has marks at every 1/10 of a centimeter. When you're taking a measurement, you always have something called an uncertain digit, which is a digit that you, the person who took the measurement, measured. So if I had this, say, red ribbon, and I was measuring it using the top ruler, I'm certain that it was at least 5 centimeters long, but this decimal here, the 1/10 of a centimeter, I have to estimate it. So I would look at that and say, okay, I'm estimating that to be about 0.4, not quite halfway, so not quite to 0.5, about 0.4. So that 4 right there would be my uncertain digit. Uncertain digits are still significant, so this number would have 1, 2 significant digits in it. If I measured that exact same ribbon with a ruler that had marks for every 1/10 of a centimeter, now I can look at it and go, okay, I'm definitely certain about the 5, but I'm also certain about 1, 2, 3. There's at least 3/10 of a centimeter, so I'm certain about that 3. And then I can estimate the digit in between the 0.3 and the 0.4. So I'm going to say it goes a little bit past halfway, so I'm going to say about 0.6. You may look at this and say, that's about 0.07. That's all right, as long as there is the same number of estimated digits, then we're fine. That estimated digit is going to vary from person to person, depending on who took the measurement. So 5.36 has 1, 2, 3 significant figures. So that uncertain digit counts as a significant figure. So how do I know, if I wasn't the one who took the measurement, if I'm just looking at the number, how many digits in that number are significant? Well, there's a couple of rules. The first rule is pretty straightforward. Any number that isn't 0 is significant. So if I just told you 7.314, any number here that is not 0, which none of these are 0, are all significant. So 1, 2, 3, 4 numbers. So all of these are significant. This number would have 4 significant digits. The rest of the rules deal with, well, what if there are zeros? When are zeros significant and when are they not? It depends on their placement. If the zeros are in between non-zeros, then they always count. So 60.052. These zeros are in between non-zeros, so they count as significant figures. So 1, 2, 3, 4, 5 significant digits or significant figures in this number. What if they are at the end? So zeros at the end of a number, also called trailing zeros, are significant whether or not there is a decimal point. So, for example, 40 or 4.70, there is a decimal place. If there is a decimal place, then that trailing zero is significant. So 1, 2, 3 significant digits. If there is no decimal anywhere in the number, then trailing zeros do not count. So 100 has just one significant digit. These zeros do not count because there is no decimal. Now, if I did put a decimal in the end there, it doesn't matter where the decimal is. It could be in the middle of the number, the beginning of the number, at the end of the number. As long as there's a decimal somewhere, then trailing zeros will count. So 100 point would have 1, 2, 3 significant figures. Leading zeros, zeros to the left of the first non-zero, which you only see when there are decimal places, are not significant under any circumstance, never significant. So 0.0032, these leading zeros are not significant, so only the 3 and the 2 are significant digits. So let's look at a couple of examples here. How many significant figures are in the following number? 3.400. The 3 and 4 are definitely significant, so the question is whether or not these zeros are significant. They are trailing zeros at the end of the number, so they're significant as long as there is a decimal place, and there is. So these get to be significant, and I have 1, 2, 3, 4 significant figures. 3004. These zeros are sandwiched in between non-zero digits, so they are significant. So 1, 2, 3, 4 significant figures in this number as well. 300 point. Because there is a decimal, trailing zeros get to count. So these zeros here count, and I've got 3 significant figures in this number. Here's one number that has lots of zeros. 0.003040. Leading zeros never count under any circumstance, so these first 3 zeros do not count as significant. This 0 here is sandwiched in between, so it does count. This 0 trailing on the end counts because there is a decimal. So those digits that do count are the 3, this 0, the 4, and that 0, for a total of 4 significant figures in this number.